Okay, here we'll begin Chapter 2. In Chapter 2, we will be looking at some more complicated features of organic chemistry than we found in Chapter 1. Here is again a review of wave properties of electrons. Okay, note when electrons move, they move in this wave-like motion. And when we use the plus and the minus signs for the wave, they refer to the phase. And so here's a negative phase where the wave is moving down, and here's a positive phase when the wave is moving up. And here where there's no amplitude of the wave, zero amplitude, we have a node, which is where the nucleus is, and that node is found right here in the p orbital. And oftentimes we use this wave function psi to describe the size and shape and the orientation of the wave. Okay, so again, the node is where we have zero amplitude of the wave. Okay, here's just talking about linear combination of atomic orbitals. When we combine orbitals between two different atoms, we get a bond that forms. When we combine orbitals on the same atom, we get hybridization, which we'll be talking about later in this chapter. There's a conservation of orbitals, waves that are in phase and add together, the amplitude increases, whereas waves that are out of phase, adding together, the amplitude decreases. And if they are exactly out of phase with each other, then they will cancel out, and so give you a node. Here, this slide deals with sigma bonding. Remember that electron density lies between the nuclei in atoms, and so a bond may form between two s orbitals or two p orbitals, or an s and a p orbital, or hybridized orbital overlaps that we'll talk about more later. The bonding molecular orbital that we'll be calling the MO is lower in energy than the original atomic orbitals. Okay, so here what the principle is that when we bond, we get a decrease in energy. So that simply means that bonding is always favorable between two atoms because we get a drop in energy. We'll be talking about the anti-bonding molecular orbital, and that's a molecular orbital where there's an increase in energy between the atomic orbitals. We'll highlight that some more when we get to that. So here is a slide on sigma bonding in some more detail. Here are two s orbitals. Remember, the s orbitals are spherical, and so here they are adding in phase, and so we get nice overlap, and when that overlap occurs, we get a sigma bonding molecular orbital where the electrons are shared between the two here. So the formation of a sigma bonding MO is when the s orbitals of two hydrogen atoms, which are these two, overlap in phase with each other. They interact constructively, that is, they add together positively to get a bonding molecular orbital. Here's the anti-bonding. The anti-bonding is when we have two s orbitals out of phase, signified by the plus and the minus s orbitals. And so when these try to overlap, they form a node, because when they try to overlap in the middle here, you get a full cancellation of electron density. and so they interact destructively to form an anti-bonding molecular orbital. And remember what happens when you do that. These will always have an increase in energy associated with them. And so here what we do is we put the two together. The bonding molecular orbital will be a drop in energy, and the anti-bonding, where we always use this star, so sigma star is anti-bonding, is a higher energy. And so we always put the electrons in the lower energy first, and so we get this energy gap between the sigma and the sigma star. Here you can do the same thing with p orbitals. If we overlap p orbitals in phase, so combining these two, we get a sigma bond between two p orbitals. And the same way we can get a bonding orbital and an anti-bonding orbital. So here are some solved problems. Here they're trying to overlap two p orbitals out of phase, so there'll be a cancellation, and so the formation of a node here. So this would be a sigma star molecular orbital between two p orbitals trying to overlap sideways to form a sigma bond. Here what we're trying to do is overlap a p and an s in phase, and so when we do, we're going to get a nice sigma bonding molecular orbital, which will be a drop of energy. Here we're trying to overlap a p and an s out of phase, and so when we do, again, we'll get this node forming between the two, and so we get a sigma star anti-bonding molecular orbital that will be of a higher energy. Here, what we try to do is overlap two p orbitals sideways, which is the formation of what's called a pi bond. If we overlap the two p orbitals in phase, then they add nicely together to give us a bonding molecular orbital that will be a lower energy. If we try to overlap them out of phase, then we get destructive for anti-bonding interaction, and so we get a pi star that forms, which is an anti-bonding molecular orbital. And so again, we get the formation of a node between the two p orbitals. Okay, so this is how we form a pi and a pi star. For multiple bonds, such as a double bond, what you get is a sigma bond between the two atoms, here the two carbon atoms, and you get a pi bond between the two atoms. The pi bond, remember, is the sideways overlap of two p orbitals. And the way we view a pi bond, so you can imagine there's a p orbital here that's overlapped with a p orbital here. What we do is we view half of the pi bond on the top and the other half of the pi bond on the bottom. And so we get one bond plus a half and a half for a double bond. So this drawing is representing a carbon-carbon double bond. If we did a triple bond, it consists of one sigma bond and two pi bonds. And we did that in class on the video. Here's some molecular shapes, okay, that I tried to draw in the video. Here they are nicely drawn for the sp3 carbon. Remember that it is tetrahedral. Tetrahedral has bond angles of 109.5. For sp2 carbons bonding together, we have a trigonal planar, so this molecule is flat, okay, and the bond angles are roughly 120. For sp carbons, Okay, the molecule is linear, so all these atoms are on the same line with bond angles, of course, at 180. Here looking at sp hybrid orbitals. Okay. When doing so, the two orbitals combine, that is the s and the p, to form two sp orbitals, and we get linear geometry. Again, bond angle 180. Okay, so here they attempt to show the picture of the sp orbital. Remember, it's a pretty fat orbital that we use here. Here they're looking at the bonding between hydrogen and beryllium. Okay, so won't spend much time on this. Here are the sp2 hybridized orbitals. Okay, so here we're mixing one s and two p's, and so what we get is sp2s, and we get 3 of them. Okay, and these hook up to form trigonal planar geometry. Okay, so here's what the sp2 looks like. You have 3 sp2s sticking out like a triangle, and then you have this perpendicular p orbital that was left over that was not hybridized. So here's some more practice problems. We'll just skip over these. The sp3 orbital, remember what we're doing is we're mixing one s and 3 of these p's, so here's one and the other 2, and so we get 4 sp3s, and remember the geometry is tetrahedral. Okay, so here are the 3 hybridizations, sp, sp2, and sp3, and their corresponding geometries that you want to remember, and their corresponding bond angles. Okay, here they did a solution for ammonia, NH3. Note it has a lone pair that's left over. Remember, the lone pair is counted as a thing, so we have a total of 1, 2, 3, 4 things on nitrogen to make the nitrogen an sp3 hybridized atom. And so these lone pair are in an sp3 atomic orbital, which is shown right here. Okay. Here, getting into the rotation of single bonds, when we form a sigma bond, that sigma bond can easily rotate. Okay, so here is the eclipsed. See how all the hydrogens eclipse each other across that bond? If you rotate this bond, you can get the staggered conformation. Okay, so we always have nice free rotation along single bonds. We do not get that with double or triple bonds. Okay, so here's the bonding pattern for a double bond. And again, you cannot get rotation around a double bond, because if you do, you would break the p orbitals. Okay. So again, double bonds cannot rotate. Okay, so here's the topic of isomerism. Molecules that have the same molecular formula but differ in the arrangement of their atoms are called isomers. The first kind of isomers are called constitutional isomers or structural isomers, and they differ in their bonding sequence. Stereoisomers differ only in the arrangement of atoms in space. We'll talk about this more in Chapter 5. So here, constitutional isomers. If we start with pentane, so here we have 5 carbons straight across. If I were to break this bond and move it to this carbon here, we would get this molecule. And you can see this has a different bonding arrangement than this, so these two are isomers. Over here, to get neopentane, I could move this CH3, for example, to this carbon, and we would get another bonding sequence. And so all 3 of these are constitutional or structural isomers. Note that they all have the same molecular formula. Geometric isomers, okay, dealing with the double bonds. We'll deal with geometric isomers later when we get into that proper part of the chapters. So we'll just skip over those for right now. Okay, dipole moments, okay, are when we have 2 atoms of different electronegativity bonded together, and so the dipole moment will always point toward the atom with higher electronegativity. If the 2 atoms are the same, we have a nonpolar bond. Okay, molecular dipole. This is talking about if the molecule has a dipole moment. And the way if a molecule has a dipole moment is if all these individual dipoles add up so that I have a net dipole. So here, all these are adding, so I get a net dipole in this direction. Okay, so I get a mu of 1 dBi. Over here, all the dipoles are in equal opposite directions, so the dipole moment cancels to give me 0. Okay, lone pairs also contribute to dipoles. If I have a lone pair, they are very electronegative, and so the dipole moment always points toward those electrons. So you can see how water has a net dipole moment. Okay, and here acetone, you have a dipole toward oxygen and then toward the lone pairs, so it has a net dipole moment. Here toward nitrogen and toward the lone pairs, so those add up for a very strong dipole moment for acetonitrile. Okay, intermolecular forces. These come into play when we look at things such as the melting point, the boiling point, and solubility of compounds. The major intermolecular forces are the dipole-dipole, London dispersion, and hydrogen bonds. The dipole-dipoles, these are the strongest, and the London dispersion are always the weakest. Okay, so dipole-dipoles, if I have interactions between 2 polar molecules, their positive and negative ends are attractive toward one another. Okay, if you have 2 negatives or 2 positives, they end up being repulsive. Okay, so a liquid or solid, the molecules are oriented with the positives and the negatives together so that the net force is attractive. And here's how we can display that. So if I looked at CH3Cl, the chlorines would be attracted to the positively charged carbons. Okay, so you can symbolize it like this. Repulsion is if you put 2 of the same ends together. London dispersions, these are also called van der Waals forces. Okay, these are simply temporary dipole moments. They're very, very weak. Okay. and these are the main force in nonpolar molecules. So nonpolar molecules are attracted, but very, very weakly, by these weak van der Waals forces. Okay, so here's an example of how these are set up. You got the electrons and protons in there, and at a temporary time and moment, you can get slight attractions between the two and get something like that. Here's the effect of branching on boiling point. When we have branching, that makes the molecule spherical, and the more branching you have, the more spherical the molecule becomes. So with no branching, you have a lot of surface area, and that will have a lot of contact points between other molecules. When you get branching, you get spherical, and so you get fewer contact points. And so this here will have the lower boiling point, whereas a non-branched will always have a higher boiling point. Okay, hydrogen bonding, it's a relatively strong dipole-dipole attraction where we have hydrogen on nitrogen or oxygen. Okay, so alcohols tend to have higher attractions or stronger hydrogen bonding than NH bonds. Okay, so here's an example of hydrogen bonding between molecules. Here you can see this has a higher boiling point than this dimethyl ether. Why? Because this can have hydrogen bonding. The ether has no opportunity to hydrogen bond because there's no hydrogen on this oxygen. So these two are isomers, aren't they? They're structural isomers, and this one higher because of the hydrogen bonding. Okay, here you see stronger hydrogen bonding in the alcohol versus the NH hydrogen bond. So it's a lower boiling point for the amine compared to the alcohol. For solubility, the rule is like dissolves like, meaning the more like the structure is, the more it will dissolve or be soluble with another. The first way to approach that is that polar solutes dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. Okay, molecules with similar intermolecular forces will tend to mix very nicely. Okay, so here you have an ionic setup here between atoms. You mix it into a water solvent. The water can easily hydrate or surround these atoms because of its polarity. If you were to put the same thing in a nonpolar solvent, these things have no way of being attracted to these positive and negative charges, so as a result this will not dissolve. It's like putting salt in oil. The salt will not dissolve. However, if you have a nonpolar molecule and a nonpolar solvent, okay, now you have similar types of attractions, and so this would dissolve very nicely. Okay, and lastly, if you mixed water with a nonpolar solvent, again, these are not like. Here you have polar water and nonpolar solid, so there's no attraction between the two. Here we have an important discussion on functional groups. Three major classes: hydrocarbons, where these are composed of carbon and hydrogen only; Compounds can also contain oxygen and nitrogen. Okay, hydrocarbons can be alkanes, cycloalkanes, which are ring-like structures, alkenes, where we have at least one carbon-carbon double bond, cycloalkenes, where we have a double bond in a ring, alkynes, where we have triple bonds, aromatic, where we have a benzene ring in the molecule. When we have compounds with oxygen, they could be alcohols, where they have a OH or a hydroxyl group. Ethers, where we have two alkyl groups bonded to an oxygen. Aldehydes and ketones, where we have a carbonyl in there, C double bond O. And lastly, carboxylic acids, where we have this functional group in there. For nitrogens, we can have amines, we can have amides, we can have nitriles,